Hello, everyone. This is Kim Parnell. Let me just get my PowerPoint slides up. Thank you very much for attending today. I think this is a really interesting application area where we have aspects of biomechanics and prosthetics meets with aerospace carbon fiber composites and the ways that these advanced materials can be utilized and taken advantage of for strength and weight in particular. Let me quickly give you an outline of some of the things that we want to cover today, and then we'll start in from this point. So first we'll give an introduction on some of the aspects of this application to carbon fiber prosthetics in particular. We'll cover some of the ways that I've utilized MSc Marc in performing this analysis, looking at the model, how the composite materials have been included, and material properties, ply drops, things of that sort, how they're taken account of, and look at some of the results and comparisons. We'll talk a little bit about fatigue testing. This is a challenging area for these types of materials, and also talk a little bit about use of digital image correlation or DIC testing associated with validation verification of results, and also getting additional insights into some of the failure modes that are present here. And we'll talk about some future expansions of this work and utilization of cloud computing. So the need for prosthetic feet, I have learned, is definitely a lot larger than I would have ever gathered, coming from accidents, injuries, our military activities in the Middle East have contributed, but certainly other things as well. We even have one of the contestants on Dancing with the Stars this year as a double amputee due to an illness. So you see it in various places, and you also see people with prosthetics living very active lives and truly being athletes in every sense of the word then. So these types of users definitely want to have a spring in their step, you should say, be strong, but be able to have good energy return and good flexibility or spring in the prosthetic. So this brings up a lot of challenges. As I said, fatigue and durability is certainly a big one, but getting that right balance between the right strength and stiffness and still maintaining low weight, these are also important constraints. Let's talk a little bit about some of the specific components of a particular carbon fiber prosthetic, names of the components, and a little bit of information on how they are constructed and designed. This primary portion of the foot that you see here is referred to as the keel. You'll notice that there is quite a bit of thickness taper in this component and in some of the others, but it's very apparent, I think, in the keel component. And this is accomplished through progressive dropping of individual plies. This keel has something over 100 plies in it, and they're progressively dropped to thin or taper the cross-section of the component. The other component that we'll focus on primarily in the analyses that I'm presenting today is the one shown in green here, the heel component. And that's back at the back, as you might guess. And this particular design has what's referred to as an overload component. Basically, it's a travel limiter, and to try to prevent overload of the heel, so to provide contact and a additional amount of stiffness and restraint against excessive deformation of the heel. Another aspect that we're going to be looking at here today as one of the important design parameters is what's shown in red here. It's just a urethane pad on the heel. There's another one on the toe, but we're going to be focusing on the heel component there in terms of thickness and length of that design component and how it affects. It's primarily there to prevent wear of the material from contact with ground or something. These do typically have a sole component that's used, and oftentimes a foot form that will be placed around it. So they are typically not in ground contact, but still that can be the contacting portion of the member through the foot form and shoe and that sort of thing. And you see here on the right one of the foot forms around. On the left is a more open prosthetic. And these are both parts of a fatigue test system, two different types of fatigue test systems. So I'm going to run these as videos just to give you a little more sense of some of the ways that fatigue testing can be accomplished. Pardon me, let me go back there. So this one on the left is more of a alternating vertical motion then, alternating from toe to foot, toe to heel for the contact then. And then here's another aspect of fatigue testing, more of a rolling contact. So you see here the platform is pivoting and making contact with the heel and then rolling through to progressive contact up on the toe then. So two different aspects, and it can be very, very difficult to get a fatigue test that is relevant, severe enough without being too severe. These are also one of the challenges that designers of prosthetics face in evaluating the designs. So let's talk a little bit about carbon fiber prosthetic design in general, what we see here on these components. These particular components are predominantly unidirectional composites. So that means that the fiber direction they have a single fiber in them, single strong axis in them, and then these plies here are oriented for these components all in the 0 degree direction or along the length of the foot or the heel member. That's the direction of primary bending. Now, a lot of times you will have alternate orientations, and off-axis plies can definitely be utilized to great advantage in composite materials to provide more stiffness in the transverse direction, to help to provide some stiffness against twisting or resistance to twisting and things like that. A couple of other comments we'll make that thin plies as compared to thicker plies can be more resistant to delamination and other types of failure mechanisms. And you can also get a strong degree of homogenization as you get the number of repeats of sublaminates up into the range of 16 to 32. This homogenization effects can be important. We'll talk a little bit more about that as well. So as I said, this is focusing on the heel component and comparing two different alternatives. Looking at this urethane pad component on the lower portion of the heel, so a thicker and shorter length of urethane as compared to a thinner and longer set of urethane, and looking at some of the aspects of each and what they represent in terms of loading onto the carbon fiber composite heel and the effects of them then. So one thing that we're going to see by utilizing a nonlinear finite element analysis are to be able to include the effects of contact and large deformation and rotation of the components. And I'm utilizing the solid shell elements in Marc in this model that allow you to specify layers of material. They can also be defined on a per layer basis, but you can define groups or layups of material of specific orientation and thickness and inside. And again, a couple of different views of looking between here. The components that we're going to look at to make some assessment of effectively overall stress levels is the strength ratio. The strength ratio is a very useful component or value in assessing composite materials where you have significantly different strengths. You have orthotropic material behavior and significantly different strengths in the different behaviors. So you can establish a specific failure criteria or assessment criteria like Sai-Wu criteria, and then evaluate a strength ratio from that. And the strength ratio is a scalable component, and it really gives you a direct read on the factor of safety relative to the strengths that you have specified. So a strength ratio of 1 would mean you're just meeting that specified strengths for your failure criteria. Strength ratio of 3 would mean that you have a factor of safety of 3 relative to those strengths then. So these animations show just a comparison, an overall comparison of the motion and response of the heel and the contact for this short and thicker pad on the left side and the longer and thinner pad on the right side. And we'll quantify these a little more, but you can definitely see that right away what might be anticipated, that you get more bending and rotation here on the left with the thicker pad, and the loading tends to remain focused closer to the ends of the heel, so that's part of what causes more bending before you ultimately ground makes contact up here with this portion of the heel. And here on the right, there is a more progressive contact effect, and the effective load or equivalent load gets moving closer and closer to the bends as it goes through. another comparison just from a different view then. And then we're going to step through a few of these pictures just to compare, and this will be for specified vertical displacement and looking at response as we go through for different views. These are all views now of the short urethane pad as we progressively step through. So progressively increasing the displacement, the vertical displacement, and how you make contact with the pad, how you make contact with the composite heel component, and then there's another contact here with the keel, surface of the keel. What I am looking at here is the overall strength ratio. So the first strength ratio, we'll look at it again here on this view. So now doing the same thing with the longer pad. Since the strength ratio is essentially a ratio relative to your specified failure and strength criteria, you can have Mentat provide just the minimum strength criteria. Some failure criteria will have multiple criteria to evaluate. Sai-Wu, for example, is a single scalar criteria. So I'm plotting the minimum first strength ratio across all layers. So that means that you look at a particular element and integration point, and then where there are multiple layers specified for that element, look across all layers at that location, find the lowest value, and display it. So it's a quick way to get an assessment where you have a multi-layer shell element specified to get an assessment of the worst case at each particular location then. And then stepping through there. So this is that longer urethane pad where you get a more progressive contact as you go through. And here's a plot to compare vertical load and versus deflection. So essentially the slope here is an effective stiffness of that heel component in the way that we're loading it here at each time. So we have the thicker, shorter urethane pad component, heel component on the left side. We have the thinner, longer pad on the right side. And vertical scales are the same. These both go to a peak of 750 pounds. And the horizontal scales also the same. We've loaded them both through the same full-scale displacement, 0.55 inches, full-scale horizontal displacement. And you see pretty clearly the overall stiffness of this short, thick urethane component is lower because there's more bending associated with it. You know, in the initial going, they're fairly similar, but it doesn't stiffen very much as you continue through the additional loading. The other urethane pad, the longer one, the thinner and longer one, goes through some pretty clear progressive stiffness increases as you go through, as the contact moves closer to the bend, and there's less overall bending then. Takes more load to provide a given amount of displacement. And so while we've compared things primarily on a displacement basis, you know, in many ways for applications and other aspects of comparison, you know, really a better way to compare, a better metric of of comparison may be to utilize an overall stiffness effect, so that you compare at a similar level of load then. But so the observations are pretty clear that there's additional flexibility in the shorter component, a lot more bending there that leads to more severe stresses and reduced levels of the strength ratio. And this is really just looking at stress aspects only, not yet delamination or interlaminar types of components. So we'll talk a little bit more about here in a moment. This other urethane pad provides more secondary contact or earlier contact. You get a lot more progressive stiffening out of it, and looks like it has some definite benefits in terms of providing additional stiffness, but with less overall bending response. And I want to talk a little bit about some testing we also did on these heel components using a process called digital image correlation, or DIC. This is an optical methodology. It makes use of multiple cameras and basically can use some sophisticated software to take the camera images and compute displacement fields, and then from displacement fields compute strain fields, so 2D strain fields on the visible surfaces of the components. So you don't get through thickness effects, or you don't get interior effects, but you do get surface effects. So like looking on the edge of these components gives you some understanding of the through thickness variation, but you don't get inside, other than that. It can be used, though, both static and dynamic testing. Is even used in drop tests and some fairly high rate dynamic types of loading scenarios. So I want to show you a few pictures and results from DIC to give a sense of some of the things that can be done. Here you'll see this heel component with these basically white speckled drops, paint droplets on here that'll be used as the tracking points by the software. So you get a rather fine pattern of dots, and with good resolution on the cameras, you can get ultimately compute good, well-resolved fields through the thickness zone. And here's some of the aspects of what you can see in terms of principal strain values, then and values as you go through the thickness of the components. Here's a principal strain value then, and this contour plot of principal strains as you go through. Also, you can compute principal strain directions. So hard to see here, but over the fringe plot, we're also superposing the primary direction associated with the major principal strain, so the maximum principal strain value. And a little bit more close-up area here. And then finally, one just before failure. So this is looking in one of the bins of the heel component, and we're up to, for this component, a load of 650 pounds. So the way this was fixtured and loaded, failure was in this order of 650 to 700 pounds in a compressive loading mode. And this is an image of the failure. So you see a few different things. You see some evidence of tensile failure on the outside, some evidence of compression, high compression on the inside. You see a number of interlaminar or delamination types of defects that are becoming apparent, and that's also a very important mode of response of this component in particular, and sometimes composites in general, that delamination or interlaminar effects can be really key. So we'll talk about that a little bit here as well. That's actually one of the next steps that I want to work on, is incorporation of the potential for delamination, to evaluate delamination in the components. And really the best way to do this is to involves quite a bit of model refinement. You know, if I want to be able to allow for delamination between any layer, basically I'll utilize a solid shell element, one solid shell element for each layer. And then this will, Marc then has the ability to generate a cohesive element between the layers, or between the thickness elements, based on meeting a criteria like a normal stress, shear stress type of criteria. It can generate cohesive elements between. So this is a good capability to allow evaluation. But as you might imagine, you know, something that has over 100 layers, this becomes a much bigger problem to deal with, a bigger analysis problem than what I had previously. So this has motivated me to also look at some of the aspects of doing cloud computing for these types of large-scale problems, and where the resources are beyond what I've typically had access to. So I want to talk a little bit about cloud computing and some of the ways that they can be obtained. So I've started doing some work to set up this next step model, this more detailed model, and utilize cloud computing kind of as defined through the Uber Cloud project. It provides really a kind of an on-demand network access to large-scale resources, and these are ones that can truly be scaled and be available, particularly for large-scale parallel computations, but even, you know, for smaller numbers of CPUs, have high memory, high disk access, and basically provide access to software like Marc as just a CAE software component that's available as a service then through the cloud system. So more traditionally, you know, you might go from desktop to a server, to a large scale system for doing analysis, and maybe these systems were internal to your organization. So really what we're looking at now is just utilizing a cloud-based server, if you will, but one that can really be configured in a variety of ways. And as I said, particularly can be scaled up on for parallel computations to chain additional ones together then. And some additional just overall view of doing different types of computational analyses. So I'm working on finite element analyses, but lots of other types of software and large scale cloud computing applications are available through this route then. And the particular vendor that I've been working with for doing this next simulation is Rescale. And Rescale has a good web browser type of interface or front end to allow me to set up a Marc analysis job and then specify the particular configuration or resource type that you need. And so really specify or set up what you need for a specific type of simulation, size and scale of simulation. So this is really becoming a pretty straightforward way to work then, to set up a model and then do the simulation of even very large scale models in the cloud, or particularly to do things like optimization and design of experiments where you may want to run a variety of parameter modifications to see the effects. This really becomes something that can all be done in relatively short time then by access to significant computer resources through the cloud. So this is the approach that I'm working on next, to incorporate the delamination into the Marc model that I outlined here today. Looking forward to getting some additional insights on it. So just to summarize some of the things that we've talked about today, particularly we've talked about simulation and comparison with experiment or test through the digital image correlation. That can give a really good understanding of results and validation of results and models, and can also open your eyes to additional types of failure modes that may be important to look at then. We talked about fatigue testing of these types of components and how some of the challenges in evaluating the right types of, or developing the right types of fatigue tests can be then. And we also talked about utilizing DIC during not only slow static testing, but also through dynamic testing. So it can be utilized for things like fatigue testing or cyclic loading and that sort of thing. So it gives some acknowledgements to groups that have been very helpful on this project to me. Freedom Innovations, a company that develops carbon fiber prosthetics. Trillion Quality Systems that did the digital image correlation testing, and also Alan Nettles at NASA Marshall was involved in the DIC testing, and then of course MSC Software for the Marc nonlinear finite element software. So thank you very much, and open it up for any questions or comments at this time. Thank you for attending.